stability. In understanding of building envelope structure, adaptive facade is the direction that designers have been trying. Adjustment of adaptive facade is related to movement of the unit component, which is huge and heavy, which will result a lot of power consumption. So the lighter material we use, less energy consumption we will have. But compared with heavy materials, the lightweight materials usually have less corrosion resistance and durability. It's easy to be scratched by hard objects in sandy or windy climates. So we hope to find a method that can make the heavy material and the light material cooperate with each other to achieve a more easier effect. I hope to get the answer in the field of bionics. As the graph on the right shows, nature gives architecture inspiration on many levels. To those the problem human beings are facing, many creatures have encountered and evolved solutions for a long time. There are not too many special structures in the anatomical composition of the section. We look at the photo.
I think they lost connection.
Can you continue on
Yes.
her behalf? Yes, thank you.
Yes. There are many researchers on the chaptology and the method of membrane and wings folding in biological papers. And here we summarize the type of folding which is very common in insect wings. Represented as by origami will be taken in the picture we shown, consisting of 3 non-parallel Y-shaped peak line and 1 valley line. Page 26.
Shinue is here, so maybe she can continue.
Yes.
Okay.
We're taking this picture, we're taking Kazuya Saito's research result as an example. It can be seen that the Y-shaped folding line is the basic unit of the membrane ring folding line. In order to better study the insect's wings, we make a classification of it. Divide the wing movement into four different basic movements, including the rotation of the overall wing and 3 types of folding, namely side folding, horizontal folding, and vertical folding. The first type we show in this picture is a simple rotation and multi-dimensional rotation. We're taking the butterfly and the less wings as examples. The second and the third type is fan fold and horizontally fold. We're taking the grasshopper and the beetle as example. The last one is vertical folding. We take the wasp as example. But the most folding wings of the coleoptera insects are a complex combination of different folding modes, such as air-wing wings based on fan-shaped folding. The other two folding methods are aided and combined with horizontal and vertical folding repeatedly. From the previous bionic design, we have summarized the following three principles that can be used in our design. There are basic folding modes, the basic driving force, and the basic folding pattern as we show. And we can draw a conclusion. The wing folding form is an overall linked configuration. It means that when we apply pressure to a specific position, the whole wing will fold. In addition to the folding method, we have also done some research on the folding structure of membrane wings. When we came to air-wing wings, the insect which has almost the longest and the most complex breath in insects, we want to know how does it ensure that its wings unfold smoothly when it opens. So we enlarge the structure of its folded part, especially the part where the peak and falling line intersect. At the same time, the existence of those elastin proteins makes the folding have an initial driving force, which allow the unfolded wings to be folded fast and more stably when they need to be folded. Use resin on this part, which can store elastic energy along the crease to promote the folding and unfolding mechanism. In studies on insect wings, let us clarify the design ideas and summarize it as the following figure. In the previous part, we discussed about how we get inspiration. From now on, Lin will show us how we made our design.
Here is our design flowchart. First is the inspiration part. Then we collect and analyze the data of the building, climate, and then we design the geometry of that objective facade. When the same inspiration, we got several geometries to choose. So we start the experimental procedure to check the shading effect of our design and choose the best of them. From here, we are going to show the design flow of our final choice. The geometry derives from the classical pattern of ladybug wings. With this pattern and the structure of the wings, which will affect the mechanism of the facade, we build two shapes. And we choose the better one, considering the geometry, construction, and the maintenance. And then we distinguish the material, make the outside material opaque and hard, the inside material soft and translucent. This idea comes from ladybug wing, where the foldable wings are well protected by the outer shell. Here shows the rhino model of the facade. In order to simplify the simulation part, we make the model in 3 states: open, closed, and semi-open. And this part is the daylight and energy simulation analysis of the design in the previous steps. Here is the basic information of the building we chose. Here shows the dress shape, orientation, and surroundings. And our building is located in Madrid, Spain, and the south and north is the main facade. Here it shows the analysis of the angle of the sun and the shadow of the building. In winter, the angle of the sun is small, which may produce glare, which requires special attention. At the same time, the buildings on the south side can hardly form a shelter for the south facade. And here shows the temperature and the relative humidity of Madrid. And this is the radiation analysis of the building. The south side is affected the most, followed by the east side. So we pay most attention to south side. Here we choose a standard room as base room and apply 3 different design cases we have made to check their effect on daylight and energy. These three cases come from the same concept that we have discovered from Ladybug. So they have the same moving mechanism and material. The only difference is the geometry. These three cases are split as three states: open, closed, and semi-open, to simplify the calculation. Here shows an analysis card which contains our requirements and criteria and all the settings. This is the flowchart of how we run the calculation and how we make the comparison. We go in 5 steps. Firstly, we calculate the three states of the three cases respectively, and then with the data of illuminance and GDP, we list the schedule for each case. And then we combine the data with the schedule and make the comparison. From here, we are going to show some comparison about daylight and energy for three cases. First, we show the UDI value, the useful daylight illuminance, and case 2 performs best with shading efficiency over 60%. And here we start to compare the DLA value, the daylight autonomy, to check the indoor light is sufficient or not. And here we start to compare the glare analysis. We set these two views to run calculations. View 1 is 45 degrees to the window, and view 2 is 90 degrees to the window. And so here shows the DGP comparison, the daylight glare probability comparison. We set case 2 has the best shading performance, and the number of hours with glare problems has been reduced by over 80%. The DGP value only shows the overall anti-glare effect. So in order to understand the glare situation of each state, we make a detailed calculation for critical time, and we focus on closed and semi-open states. We found that even under closed states, glare can still be a problem. The value is over 0.5, so we need to consider the transparency of the material. And here shows the energy consumption of each case. We make some graphs to make the comparison clear. Here shows the geometric comparison. We compare two properties, the presentation of opening and the visibility. And so case 2 and case 3 are better. And here we show the daylight comparison. We compare two properties, the indoor light quality, which is depend on the DLA value we have calculated, and ability to avoiding glare. And case 2 and 3 are better. Here is the energy consumption. We compare two properties, increased heating load and the reduced cooling load. And also case 2 and case 3 have a better performance. So in conclusion, we found that case 2 is better than case 1 and case 3, but case 3 can also be a choice. So to improve, we give two ways. First is change the film material to opaque. The second is to change the pattern of the facade. And here is the pattern to be changed. To check the effect of the pattern, we run the simulation again and finally find that pattern to give better performance at noon. After changing the material of the film, as we said before, we make an improved calculation for case 2 and case 3, and name them as case 2 opaque, case 2 new opaque, and case 3 opaque. And we repeated the previous simulation and calculation process. After completing the comparison of UDI, DLA, DGP, and the laws, we got this result. In geometric part, case 3 does not perform good. And in daylight part, case 2 is the best. Case 2 opaque is best. In energy part, case 2 new opaque is also the best. And we are also considered other patterns and find none of them are better than pattern 2, but they can be a choice for other orientation themselves.
Then we go to the last part, implementation. It's including nodes movement, actuation, material, and structure details. First of all, the adaptive facade is dynamic. So to fulfill this kind of adaptive unit, we need to know the way that how it moves and preset the check for it. For better description, we rename each node as the letter in point A, B, C, and D. We can see that the entire component is regular, so rotating a diamond-shaped geometry by 120 degrees and 240 degrees, then we can get a regular hexagonal geometry. The movement of point A is like a slider. It moves along a straight bar behind the facade. Point A is an active point. It's controlled by a monitor, and the direction of movement is controlled by a link of gear system. While point C's moving path is like a curve, which moves vertically with the main surface through a special shaped slide, and the connection between those two shell material is a four-part shaped hinge. It can provide the stability and special way of movement. For the H connection of AD and CD are working in the way of hinge. Here we choose two ways to fulfill it. The first one can be found easily in the market. The second one we use the lightweight material wrapped around a bar connected to the shell materials. The connection between lightweight material is different. We use the method of airbag that inspired by the resilient of insect wings, because it can make the material more durable. At the same time, the airbag is also an actuation. The pump at the center of geometry can provide a part of actuation for the structure assisting the unit a smoother closing and opening process. When the air is pumped into the airbag, it can give a lateral force to the central laminar layer, controlling it to fold. When the air is drawn out from the bag, the facade will unfold it. One thing we need to mention is that the airbag is secondary of actuation because it's hard to use these small components to push those such huge and heavy facade. The laminated principle is similar with the insect wings membrane. The main reason that we use it is this method could provide the durability and let the whole structure folding based on the creases we presetted. Here we can see the blow-up diagram of it. This laminated layer are composed by different materials. To verify this, we use spawn and airbag simulated this principle, and it works. We use pump to inflate the airbag, and we can see that after pumped, the airbag pushed the spawn to deform according to our expectation. And here is a video about verifying the airbag system. Since the material in the market is not easy to find, we enlarge the model's ratio to 5:1, which means prototype is in 5 centimeters thickness, where the real laminated layer is in 10 millimeters. Besides, to verify the feasibility of this geometry, we made the prototype. We use gear system simplified the slider system because this is best and simple way to test our geometry. This is the 3D model and some parameters information before we did the laser cutting. Thanks to this plugin for allowing us to make more accurate model and ensure the precise rotating of the gear and rack system. Here is the video from backside view. And it cost us around 15 minutes to fulfill the opening and the closing process. And we can see after rotating, each node can move towards or from the other side of the center point. And this is the front side of the facades looks like. With the requirement of hardness, compressive, and tensile strength, we choose CFRP as the shell material, where the light laminated material is composed by PVC coating, lighter polyester fabric, and glass wood or glass foam. This lightweight material could dramatically decrease the weight of facade itself, thus saving more energy from the moving process. The sensor we mainly considered is solar radiation sensor. It can be put at several places in front of the facade's elevation in order to monitor real-time data. Once the value over or under the threshold we set, the system will let the facade open or close. We use stainless steel structure to combine our design unit geometry together. And for the connection, we use double angle cleats riveting with the HEA beams unit to make sure the facade system are well connected with the main structure of the building. Those are some details of the facade. The height of hexagonal geometry units is 2.4 meters, and the distance between facade system and the building is 1.2 meters. The other information refers to thickness of each layer and some other components. The arrows shows the way how it moves. There is the rendering picture from inside to outside, and after installing the facade, the building looks like this. Finally, thanks for your watching, and we would like to say thanks to all of you, our professor, our classmates, and Politecnico di Milano. Much appreciated. And this is the end of our presentation. Thank you.
Thank you very much.
Thank you.
And we have the opponent here in the room is again Professor Masera.
Okay, thank you guys.
Thank you,
I
Professor.
enjoyed it. Let me find a way that it works. No. Who knows? Okay. Maybe you can hear me.
Yes.
I enjoyed reading the work, and I was saying I also seen some prototyping that I think I didn't find in the report, so that's very good, and it actually answers some of the questions that I had about the practical implementation of your idea. One thing that the prototype and also the final renders, maybe it's just a general remark, is that very often, and it's generally for all students, of course, for all preliminary studies, most preliminary studies, is that the assessment of and so on, they're all based on the presence and the behavior of the actual shading element, and very often the structure of that is supporting the element and support movements, the moving gear, so on, are often neglected. But they end up taking space, and they end up cutting off natural light. For example, when you imagine big structure is placed on the facade. So this is something that probably, like, for example, of the evaluations should be considered. So maybe a next step or some after you understand more the prototype and the type of structure that would support the elements and their movements, then would be like going back iteratively to how they are affected by these additional like metal structures, and certainly will filter the light. Okay, so general remark. So say it doesn't need any answer from your side. Okay.
Thank you, Professor.
Good. Thank you, guys.
Thank you,
See you
Professor.
later for the ceremony.
Thank you.
So I try to speak. So we're trying to do our best with these problems. Anyway, the next thesis will be presented by Rossella Scalise, right? And Alessandra Accatti. Okay, I can see you. This thesis is.
Hi, morning.
Hi, nice to see you. The thesis has been, let's say, guided by Professor Marco Pesenti again, and is a comparative study of two BPS tools for the analysis of a dynamic facade. Also, in this case, he's really sorry, but for family reason, is not able to join us today, but we will have time to comment and discuss your thesis in the end. Okay, so you can start presenting. Who is going to share the screen?
Alessandra is going. I cannot hear her. I don't know if you can.
Who is Rossella or Alessandra?
Alessandra,
Alessandra condivide lo schermo, ok.
Yeah. Okay, can you hear me or not? Yes. Okay, perfect. Sorry, I couldn't hear me.
We hear a terrible machine noise, but we were seeing the but now it's gone. We don't see the slides in. Okay, maybe they're coming. Okay.
Okay, perfect.
Okay, now we see it. Okay.
Good morning. We are Alessandra Rossella, and today we are discussing our thesis work. The title is A Comparative Study of Two BPS Tools for the Analysis of a Dynamic Facade. In this slide are collected all the topics that we are going to discuss. Starting from the main aims, we are going through the different steps, and then we are finishing with a critical comparison of the analysis. BPS stands for Building Performance Simulations, and they are softwares that are used in the building fields to simulate the different aspects. The two software used for our study are ISV and Rhinoceros 6. The simulations are performed on a dynamic facade, focusing on the daylight analysis. And this was done starting before with the analysis on basic shapes, and then analyzing a more complex case study as the one of the dynamic facade. The aim of the works are identify the causes that lead to differences and understand their potentials and limitations. This was done through target analysis and critical comparisons. In particular, the question we want to answer is, can ISV cover the broad functionalities of Rhino? As already mentioned, the two software used are ISV and Rhinoceros 6, since both are able to perform analysis on complex geometries. In this slide, it's highlighted the modules of ISV and the plugins of Rhinoceros 6 that are used for environmental, daylight, and energetic analysis. Focusing on daylight, ISV use FluxDL and Radiance IS, while Rhinoceros 6 can exploit DaySim and Radiance. It must be added that ISV is a software that focuses mainly on the energetic field, while Rhinoceros, thanks to the use of the plugins, can cover a wider range of analysis. In the first part of our work, we have done a literature review in which we collected the limitations and the potentials already identified that are useful for our work. Considering the geometry, the main difference found regards the modeling interface and the curve geometries. In fact, ISV has big limitation when modeling and when analyzing curve geometries, while Rhinoceros have more potentials also thanks to the use of NURBS. Considering then daylight, both of them can exploit can use the same sky models and the same calculation method. In particular, it was used the climate-based daylight modeling when we are analyzing the dynamic metrics, when we are calculating the dynamic metrics. Starting with a weather file and with the subdivision of the sky in patches, through daylight coefficient method and ray tracing method, it was possible to calculate the different metrics. Before analyzing the dynamic facade, we decided to analyze a simpler case to see which were the limitations in this case. The shapes analyzed were a square, a cube, a circle, and a sphere, and all of them were modeled with the same dimension on ISV and on Rhinoceros. In these slides is shown the graph of the annual radiation on the basic shapes measured in kilowatt-hour over square meters. In particular, is highlighted the percentage difference between the results. It must be up that the results were obtained in different units, and in the two software we used different radiation models. one simplified for ISV, and a cumulative sky model in the case of Ladybug. As we can see from the graphs, the higher difference can be found in the sphere that reached the 13% difference between the two softwares. This difference is due to the big limitation that have ISV when drawing a dome, a curve geometry, or a sphere. In fact, in this case, in ISV, to evaluate the results was necessary to sum up phase by phase. And for this reason, it was necessary to simplify the shape of the sphere. And this was done also on Rhino to compare them. The other limitation consists in the fact that when analyzing the sphere, the bottom part of the sphere is not considered, because it's considered like it is not reached by the solar rays, and this can cause an underestimation in the results. In this slide, it's possible to see the graph on the total illuminance of these shapes evaluated on the external surfaces. In this case, it was used the same sky typologies, CIE over cast psi, and the same calculation engine, Radiance. As we can see, the major difference are found in the vertical surfaces, since the two programs evaluate them with a different method. From now on, we are gonna discuss about the case study. The case study is an office building. It's located in Sevilla, and Sevilla is classified as a Mediterranean climate. The office is oriented southeast, and this orientation was chosen after evaluating the greater radiation direction. The dynamic facade analyzed is the wave facade. It is made by a textile material, and is characterized by a rototranslational mechanism. On the left part of the slide, it's possible to see the detail of the mechanism, while on the right part, it's possible to see the three configurations used in the analysis that are closed, semi-open, and open. In here are then collected the room characteristics useful for the analysis. In particular, the office is for 2 users, and the occupancy time goes from 9 AM until 6 PM. And then are collected all the information about the geometry dimension. On the bottom part of this slide are reported the optical properties useful for the dynamic analysis that characterize the different surfaces of the office. Here then are collected the indexes that will be analyzed, highlighting the part that is acceptable and in which range they are acceptable or not. These indexes are illuminance, daylight glare probability, daylight factor, useful daylight illuminance, spatial daylight autonomy, and annual solar exposure.
From now on, a detailed comparison of the analysis is reported. For what regards the climate, since the same APW file was used between Rhino and ISV, we obtain equal results of some environmental parameters, whereas different results were obtained for what regards the vertical surfaces for the radiation analysis. Instead, regarding the geometries, the two software have different ways of modeling the curve, rotating the geometries, and managing the layers. And in the right bottom part of this slide are shown the front view of the wave facade drawn on ISV and on rhinoceros. In this slide are shown the inputs and parameters used for the analysis, and from the images it is possible to see the working plane area, the sense position for the glare, and the grids used for the daylight calculation, one for the analysis and the other one to display the results. This slide instead is useful for the comprehension of the 4 different configurations analyzed. In fact, we did the analysis on the base case without the wave facade, and then on the open, semi-open, and closed configuration of the wave facade. So the first parameter analyzed was the illuminance.
And in this case, it is important to see how ONEB presents a higher weighted average when compared to ISV. In this case, on a specific day at a specific hour, on the 21st of June at 12 p.m. But in detail, going more in detail, it is fundamental to see that higher illuminance values were obtained close to the opening on ISV, as visible in this bottom part. The following parameter was the daylight glare probability, and it was we conducted the analysis both on June and in December. And in here, I reported the December results. We obtained almost equal values between the two programs, but a small difference could be due to the inaccuracy of the angle of view set in the two programs, because they could not be set in an identical way. And in the right part of this slide are reported the screen captures of the fisheye of the semi-open configuration, both on ISV and on rhinoceros. The following parameter was the daylight factor. And also in this case, when compared to, when the two softwares are compared, HoneyBee presents a higher weighted average respect to ISV. In this case, the daylight factor was analyzed annually. And it is fundamental to say that on ISV, the daylight factor could be calculated in 3 different ways. In here, I reported the values obtained with the custom settings. So as we just said, on ISV, it could be analyzed in 3 different cases, and they report very different results, as this is visible on this table. So while the custom parameter could be chosen by us, case 1 and case 2 were had the inputs obliged by the program. So from now on, these parameters had the input which could not be changed by us, and therefore we were obliged to use the custom parameter used by the program. The first one was the useful daylight illuminance, and in this case we reported the 3 ranges: the useful daylight illuminance lower than 100 lux, between 100 and 2000 lux, and higher than 2000 lux. For what regards the first range, so a UDI lower than 100 lux was obtained in the closed configuration on HoneyBee for a higher period, as visible in the first graph. Instead, from the other two, it is visible that ISV reaches more often higher illuminance values, and this could be due to the different parameters considered, which could not be changed by us. For what regards the spatial daylight autonomy and daylight autonomy, instead, both want a minimum threshold of 300 lux. While the spatial daylight autonomy considers the percentage of area in which this minimum threshold is reached, the daylight autonomy considers if this threshold is reached for at least half of the time considered. So from the first graph, it is possible to see that the semi-open configuration presents dissimilar values between the two software, reaching an 18% of difference, while in the second graph, we show that we obtained similar results despite the different input settings. The last parameter analyzed was the annual solar exposure. And we can see that we obtained small differences in all cases, in particular in the closed configuration, in which we reached a 13% difference. Also in this case, it is important to say that on rhinoceros, the annual solar exposure could be calculated in 2 ways, using a mathematical string on HoneyBee or direct command on HoneyBee+. Since it was fundamental to insert our custom parameter, we selected the mathematical case, so with HoneyBee. This slide instead is used for for summing up the results. And the minimum acceptable value set was 15%. And as visible in here, the only parameters that exceeded this value were the daylight factor, the useful daylight illuminance, and the daylight autonomy. For what regards to the daylight factor, a 32% difference was obtained, but this was due because we obtained very small values, and therefore this percentage difference could be overestimated. For what regards the UDI, a 23% difference was obtained between in the base case and in the closed configuration, and this could be due to the higher parameter inserted on ISV related to the parameters which could not be changed. For what regards instead the daylight autonomy 18% difference, this could be due to the curvilinear shape of the semi-open configuration, which, as we saw, can cause problems on ISV. So now we can answer to the question previously asked in the preface of this work. And by doing so, it was fundamental to define the potential and the limitation of ISV when compared to Rhino. So for what regards the potential, they regard the ease of use and the reading of the outputs, whereas the limitation regarded the drawing of complex geometries, the urban scale analysis, and the impossibility of conducting the dynamic analysis of more than one configuration. Moreover, since ISV is a commercial software, some of the inputs are not known, and this could be a problem when doing some comparison work like the one done for this thesis. So as a conclusion, we can state that ISV and rhinoceros are comparable for what regards the daylight analysis, because we did not obtain major discrepancies between the results. Therefore, ISV can cover the broad functionalities of Rhino. Thank you for your attention.
Thank you very much for your presentation. The opponent of this thesis is Professor Andrea Manini, who unfortunately is busy in the other room. And we are trying to summarize a little bit his comments about this work. In particular, he has some concerns about the, let's say, the methodological approach, in particular related to the methodologies or the calculation, the calculation methodologies who are behind the simulation engine. Because in order to make this kind of comparison, he would like to understand if you took into account the simulation engine of the different softwares you compared. And another point is related to the dimension of the shaping element, of the shading element, because just to understand if there could be some side effect that may affect the overall analysis. Shading element. Did you check my, did you? Is it clear?
Yes. For what regards the first question, of course, we analyzed the engines that are used in the two softwares. And for this reason, in this case, we highlight the fact that they were identical, and in the other case, they were not. In some cases, it was possible to insert the identical settings, and some other it was not. We tried to understand when it was possible to insert the same settings, which are the other cause that can impact the results. When it was not possible, we just highlight this fact. So yes, say that in this case, it was impossible to do an acceptable comparison it was possible just to highlight this fact that it weren't the same.
Yes, we try to highlight also that ISV is a commercial software, and therefore we cannot like change any parameters inserted like on Rhinoceros, because Rhinoceros is a huge software and it has the possibilities of inserting every parameter wanted. So for what regards the possible ways in which we could change them, we tried, as Alessandra was saying before, we tried to focus on that.
For the second question that regards the characteristic of this shading, also in here we insert all the optical characteristics, the thickness, everything in the same way in the two software. Then we don't think that could be the problem could be related to that.
Okay, thank you very much. We have no other question from the jury.
Thank you.
Thank you.
Thank you.
See you later. The final ceremony. Now we can move to the next thesis with Rafaela Monteiro. And I ask to Professor Gabriele, who is the supervisor, together with the co-supervisor, Professor Giostra, who is here today to present thesis work.
Thank you, Julian. It's a pleasure to say hello, bom dia, to Rafaela.
Bom dia.
Hi,
Morning.
good to see you. But I saw that you were connected. Rafaela is connected from Brazil. She's like 6 hours behind us, if I'm not mistaken. I saw she was connected already like at 9:30 a.m. So you were worried about having to wake up too early. You did wake up early, actually.
Wow.
So let me see if move improves. Seems like it's a radio problem. I hear some noises. So this work, which was actually co-supervised by me and by Professor Simone Giostra, who is here. I'm just here standing and written down as, in the system. That can be only one, actually. But, this is really a joint work, and it's part of a string of works which derives from somehow the big question of form influencing. If there are ways or to predict or identify shapes, and I will detail what shape means, that have intrinsically better performances than others. We've done that on facades in the past. We've done that looking at outdoor comfort, and that's Ludovica Rossi's work that was discussed yesterday in the architecture engineering track in Lecco. And today we are looking at Rafaela's work, which is about essentially, I would say, the shape of cities or shape of neighborhoods. So how volumes are arranged in neighborhoods and how different volumes influence contrasting parameters, because of course the interesting things is looking at a multi-dimensional analysis in a way, and not just looking at one parameter, which might lead us in some specific directions and saying like obviously that solar potential is bigger when it is smaller and buildings are more far away from each other. But trying to look at different parameters which might carry us to a more interesting and more complex and layers of reasoning. This is also the collaboration. You see that in the slide with Pratt Institute, New York, where part of the original discussion was made and where the case study is actually located. It's in Brooklyn. It's in one lot in Brooklyn, New York. So we see how different arrangements of volumes in a specific area with a specific climate influence some parameters. I'm not adding, probably already spoke too much. I don't want to spoil or take away anything from Rafaela. So Rafaela, the floor is.
Thank you, Professor. Can you hear me fine?
Yeah, maybe you can't hear us because the microphone is horrible. We hear you. Thank you. Great.
Okay. So good morning, everyone. My name is Rafaela Monteiro, and I'll be presenting my final thesis for the Master in Building Engineering, which is named Building Massing and Performance, a guideline for early-stage design, analyzing energy demand, daylighting, and solar potential. It was done under the supervision of Professor Gabriele Mazera and Professor Simone Giostra. So this research is part of a collective effort to address energy efficiency in buildings that involves Politecnico di Milano and the Pratt Institute in New York. And we also have been collaborating with Task 63, the solar neighborhood planning of the solar heating and cooling program. The reason why we do and address these matters is because the building sector is one of the sectors that contributes the most for the event of climate change. For instance, contributing up to 30% of the global annual greenhouse gas emissions. But also, on the other hand, it has a great potential to mitigate and deliver significant and cost-effective design strategies.
Well, for instance, we apply passive design, passive strategies aiming for energy savings. We can improve the envelope thermal performance. We can improve the efficiency of HVAC systems, and so on. And that's why we are trying to build up the knowledge on the energy-based form optimization in the design of neighborhood of buildings. So here we will be exploring the massing and the role of energy, the role of geometry in reducing energy needs in buildings. Therefore, the objective here is to find if typologies do present a fundamental energy-related characteristic that makes the building massing a determining factor at early stage design that will influence the entire building performance. We will be studying three typologies, towers, courtyards, and bars, on regards of three performance indicators: the energy demand that accounts for the heating, cooling, artificial lighting, and appliances, the daylighting and comfort conditions, and the solar potential, which is the ability of a building to receive the solar radiation and produce solar energy from that. It's important to highlight that these indicators are equally ranked here because combining them is working to find an optimal balanced performance. We will be touching at three scales. First of all, the urban scale and the massing of a residential neighborhood, then the building scale and the daylighting and energy conditions, and after all, the envelope scale by understanding if the optimizing the envelope has any effect after the massing is decided. So all the case studies are generic, but they were built with similar, with the same aspects in order for them to be real and comparable. The climate is located in New York, and the weather data used was from LaGuardia Airport, which is a climate zone 4A from the ASHRAE classification of mixed humans. The program is residential, and a window-to-wall ratio of 0.3 was decided to be in accordance with the program. As you can see, for instance, on the picture on the right, if we have chosen a WWR of 0.7, it would be more in accordance, for example, to an office building. The same floor-to-area ratio equal to 3 was decided for all the case studies, which means that even though they have different dimensions and they vary in width and depth, they will also vary in height and number of floors, which will end up on all the case studies having the same square footage. The simulations were placed in an urban context, with the center plot being the main one, but surrounded by 8 other blocks that mimic the behavior of the center one. And this center one is the plot area of 100 by 100 divided in a grid of 5 per 5 meters. So the arrangement for the towers, it can have up to 2 to 4 buildings on the plot, both in X and Y, and the dimensions go from 10 to 25 meters. The courtyard is a perimeter building that varies in depth from 10 to 25 meters. And the inner patio or the courtyard can have no division, 1 or 2 divisions, both oriented east-west and north-south. The bars can have 1 to 4 buildings on the plot, either oriented east-west, north and south, and the width varies in a 5-meter step and the length in a 10-meter step to preserve the form. The building properties are all the same, using the U values recommended for climate zone 4A by ASHRAE. That makes all the cases comparable and able to understand how they relate to each other. It's important to highlight the occupancy schedule was changed from the previous one, because before the COVID-19 pandemic, we all assumed that we leave the house to work during the entire day. So now, after we are considering the scenario after the pandemic, where maybe we account for some working from home, so we have 50% of occupancy from 9 to 6 p.m. So the research is divided in 3 parts. Firstly, we evaluated 312 case studies considering the 3 typologies, and we understood trends and outputs from the massing. Then we go into a more detailed and refined analysis, selecting the best performing cases, which are called champions. After that, we go further into the envelope scale, understanding if after the massing is defined, how much room for optimization there is. So the first chapter is all about answering a very long-lasting question in building architecture. How much form affects energy performance? Is there any best performing typology? For that, we evaluated this large pool of cases, assuming the energy demand as the annual heating and cooling thermal requirements in kilowatt-hour per square meter. The daylighting condition is evaluated using the metric daylight factor, which has some limitations, but is able to give a pretty good idea of the daylight conditions in a time-wise and computational possibilities. The solar potential is accounted here in the first chapter as the amount of radiation falling over the envelope, both facade and roof area. Here we can see some results for the towers, where 128 cases were simulated. On the left side, you can see on the darker dots the case with more towers on the plot, up to 12. And on the light dots, you can see the cases with fewer towers on the plot. Regarding daylight, we can see the daylight factor decreases with more buildings on the plot and as the plant floor becomes deeper and shorter, which is in line with the rules of thumb for passive zones and daylighting. In terms of energy demand, we can see that as the plant floor increases dimension and the building is lower, less energy is required per square meter for heating and cooling. And on the contrary of daylight, the number of towers doesn't seem to affect the energy demand, which means that for that, the main driver is really the plant floor dimension. In terms of solar potential, on the top right corner of the graph, we can see the best performing cases where we have very tall buildings with no obstruction and shallow plant floors. These buildings that take the best advantage of solar radiation are also the worst performing in energy requirements for heating and cooling. For the courtyards, we are more limited on the cases to fit inside the plot. We have 16 cases simulated, and the results are here clearly clustered by that, where you can see that this is the main factor that affects both daylight factor and energy demand. The cases with depth of 20 and 25 meters doesn't reach the minimum 2% acceptable for the daylight factor, which means that the 10 and 15 meter cases are the best performing for daylighting. For the energy demand, we can see that the 10 meter ones are the worst performing, but there's a big step to the 15 meter ones, which is 30% of difference in energy. And this step decreases as it goes from 15 to 20, having 10% only difference. And then from 20 to 25 meter deep cases, only a 4% difference, which is basically neglectable. On the solar potential here, it's important to highlight that the courtyards have a big plant floor area, which means that they don't need too many floors to reach the FAI equal to 3. The tallest one has 19 floors only. And therefore, the main driver for the solar potential is the roof area and not the facade, which means deeper the building, higher the radiation capture. For the bars, we had 168 cases simulated with up to 4 buildings on the plot. And we can see that daylight factor decreases as the building count increases, which is the effect of overshadowing. And daylight availability is also heavily dependent on floor depth, having the best performing cases of 10 as the 10 meters, which are also the worst performing for the energy demand. With that, we can see that also here the number of buildings doesn't really affect the energy requirements. If we look at the same case, same dimensions and same orientation, having 1 or 3 bars on the plot, it doesn't really make any difference, which means that energy use is less sensitive to overshadowing and much more dependent on form factors. On the solar potential, slender and taller buildings have a good solar potential and good daylighting conditions, as we can see on the 10 meter cases on the graph. And as the buildings get deeper and the count of buildings on the plot increases, as for the cases of 4 bars, the main driver becomes the roof area for the solar capture, which means that they will also have a good solar potential. Then we can compare the 3 typologies, and we will see that the towers present the highest energy demand, as well as the highest daylight factor average. The bars present a low energy consumption as they have fewer floors and become longer, and the courtyards seem to have the best ratio energy use over daylight factor. But on the other hand, there appears to be a ceiling on the daylight when you compare to the other 2 typologies. At the end of the chapter 1, it didn't really provide a final one answer. It shows trends and trade-offs, but still the result was a bit subjective. That's why we move a step further in seeking for a final answer. We then reduce the number of cases to be able to analyze it in a more detailed way. And for that, we go through a filtering process. At this second chapter, we will transform what was solar radiation into active systems, assigning a photovoltaic system to cover for the electricity demand and a thermal collector system to account for the domestic hot water demand. And they are distributed according to the solar radiation threshold falling on the surface. On the energy demand side, we assume some HVAC systems that makes it able to offset the energy demand from the production. It's important to say here that so far for this filtering process, the artificial lighting electricity is not accounted in the daylighting, it's not based on the daylighting condition, but is based on the program and the square footage only. So a building is declared a champion if it covers at least 50% of the energy with the energy demand with renewables. The daylight factor is above 2%, and the final electricity requirement is less than 25 kilowatt-hour per square meter after offsetting the 3D production. And then we end up with 25 best performing cases, which you can see highlighted on the graph from the typology comparison. And from that, 10 cases are towers, 8 cases are courtyards, and 7 cases are bars. And it's curious to see that mainly the depths of all the buildings that perform the best are 10 and 15 meter strip cases only. So here we are able to perform a much more refined analysis, offsetting the energy demand from energy production. And here, at this point, we are able to use the climate-based metric to understand the daylighting conditions. We took the LEED criteria as guidelines, so we are using spatial daylight autonomy, which the best range is above 75%, and annual solar exposure, which with that LEED requires less than 10% of glare risk. So here, because of this metric that is more refined, we're able to account for daylighting and the consequence of electricity for artificial lighting in the energy demand as well. So we can see here the results for the champions after this detailed analysis. And we can see that the bars and courtyards perform similarly, both in energy use and daylight. But the courtyards have a greater solar potential, which makes the final energy use to be lower. The towers have an advantage of excellent solar potential, which allows a high energy use to be offset and produce a good result. It also performs really well in daylighting. The bars seem to be the least performing typology, with the highest final energy demand and average to poor daylighting conditions. So we know that there is a class of building typology that performs better than the others. The question after that is, how important is the initial building design in respect to the entire design process? Once the designer chooses the massing, can the performance still be improved? And that's why we move to stage 3, where the idea is to improve the previous performance and to test some well-established design strategies to see how much they can be optimized. So we select the best performing case from the champions to be evaluated here. And we have a tower with 1 tower on the plot, 15 per 10 meters, the courtyard with 2 divisions and a depth of 10 meters, and the case of 3 bars oriented east-west, 100 by 10 meters. And we will play with 3 aspects of the building: the insulation and the envelope performance, the opening distribution and the WWR, and the envelope surface by tilting or deflecting it. And then we compare to the results of chapter 2 to see how much they have improved. For the case of tower, we had a big problem of glare, so we added overhangs to the top. The envelope surface was tilted towards the sun to improve solar capture, and the WWR was kept the same, but the openings were redistributed. We also improved the opaque facade thermal performance. And from that, we got a really good result where we have some decrease in SDA, but it is still a very good condition. But the PV annual production increased a lot, which meant a final energy use of 0 kilowatt-hour per square meter and a final energy production of 36 kilowatt-hour per square meter, which means this is an energy plus building. Then for the case of the courtyards, some overhangs were added to mitigate glare. The PV surface was tilted 30 degrees towards the south. The facade thermal performance was improved both in opaque and glazing. And the WWR was changed from top to, according to the floor, from top to bottom. And the openings were redistributed as well. And for that, we solved the main problem from before, which was a low daylighting percentage for SDA of 65. We were able to increase to 86, which is falling under the best range for least point. The final energy use was not really affected, from 7 to 6 kilowatt-hour per square meter. And here you can see that the daylighting conditions was improved, both in general, but also in distribution. And then for the cases of bar, the surface was tilted towards the south to improve solar capture. The same strategy with the WWR and the opening distribution was applied, and the same facade thermal performance was improved. And we had some improvements both in SDA from 69 to 86, and also in final energy use from 19 kilowatt-hour per square meter to 16 kilowatt-hour per square meter. From that, we can conclude that the bar seems to be reaching a ceiling in terms of optimization. It's not really performing so well as the other two were, and were showing a lot of room to optimize it. So we can compare the results for the 3 optimal cases, and we can see that, I don't know if you can see my mouse, no. Well, for the tower, the SDA has decreased, but the solar radiation improved a lot from the orange line to the purple one. And for the courtyard, we can see that the energy stayed the same, also the solar production, but the SDA improved a lot. And for the bar, we had some improvements, but not really significant. It's important to remember here, the tower became an energy plus building, which is a significant thing. Then for the courtyard, we have a very, very low final energy demand, which means that with further optimization, this might become a zero energy building. And the bar is still the least performing typology for even after optimization. And with that, I thank you for your attention, and I hope I was able to give you an idea of the work.
An applause.
Thank you very much.
Thank you, Raffaella. Congratulations. Parabéns. And we asked Professor Graziano Salvalai, whom maybe you don't know, but he's a colleague of us teaching in the Lecco campus, in the area of envelope and energy efficiency, and he appreciated your work. And there was a mention which made me particularly happy, I have to say, about your ability to summarize and show the data. We know, you, Professor Giostra, know how much data you had,
yeah.
How much we struggled to present those diagrams in a way that could be understood, because there were really tons of different cases that had to be presented based on 3 parameters. So I'm particularly glad that Professor Salvalai appreciated, which means that the results were understandable to a third party. So that was, I think, very, very rewarding. Simone, do you want to say something? Co-supervisor.
I will, just very short. I think Gabriele already covered the ground, and you did, I think, very well in presenting the data, which I think, if it's probably true in most cases, this is definitely a very challenging work to present in such a short time. And I just think it's really foundational, the importance of this work in terms of what we can, in a short period of time, achieve, what you did achieve, and what we can in projection in the next couple of years. We might actually, and I'm one of those believing that we might be able to get the final answer. I know that would be the end of architecture as we know it, and I'm looking forward to that moment. but that's just my own preference. I think the first part is very interesting, but somewhat more predictable. I think the kick in the project, so to speak, it would be the second step where you do arrive to, it's no longer a trade-off. It's no longer, oh, whatever you prefer, or it depends on the client preference. But it's really, I think, you come very close to a moment where you have just one number to characterize a urban mass. And that's awesome. I think that's as close as I know that we got to defining energy wise a urban design. And then the third, of course, is I think the third part is interesting, but of course is just a first stab, which will probably be the one that suggests the most potential for a continuation. I guess I didn't really have a question.
If I can
just comment. Can you hear me? Okay. I cannot just comment because we developed a thesis subject in this main area, and one of the possible ideas to use urban mass, we developed this thesis in cooperation with Professor Bana Meide in Chinese University of Hong Kong. And the main issue in Hong Kong is to study the urban mass in order to deal with the urbanity island. So all these parametric analysis related to the shape of the buildings were integrated with parameters at the urban level in order to guarantee urban canyons and so to have natural ventilation. In Hong Kong, due to some studies of Professors Edward Ng, they have another parameters, which is the sky view, which is a parameter which, let's say, gives some numbers related to the overshading of other buildings. So, and the idea was to optimize the shape of new development in order to reduce the overall impact at the urban level. And it's a very interesting field of research, because working at this level, you are able to solve issues at the urban and even support decision-making processes at both private and public level in order to understand which direction to go. Okay, I can stop now. We have the last presentation by Ahmed Karam, a very complex topic. Thank you.
Thank you very much.
So the final ceremony, I guess 10, yes, a bit late. So just wait for us and we will be here. So for this reason, the last presentation of today by Ahmed will respect strictly the 15 minutes. I'm saying that because the topic presented by Ahmed, which was strongly, let's say, strongly wanted by Ahmed himself, is related to an exercise of convergence. So I really hope that you will be able to summarize your work in only 15 minutes. It's a challenge, but you can do that. Please share your screen.
Hello, good day. Hello?
Ahmed, can you share the screen, please?
I shared the screen, but I don't know if you can see it or not.
No, we can't.
Mm.
Tu lì sei...
But can you see me? Can you see me and hear me? I think you can see me and hear me.
We can see you and hear you. You're up there, but we don't see any shared content.
Okay, I'll try again because
yes,
it's
please.
like
yes, please.
Okay. Okay, is it okay now?
Nothing happening, unfortunately. But maybe what we can do, Juliana, is if we have this presentation uploaded in the system, maybe what we can do is you share your screen.
I shared my screen and I shared an application also, the PDF that I'm trying to show.
But it doesn't really show any shared content, anything. I mean, maybe you see us, we are still in the grid view with the users.
Okay, I'll try it quickly and do it with my iPad.
Okay, if not, if we should. Okay, try with your iPad in the meantime, and otherwise we do a workaround, a different workaround. Ahmed, we try a workaround. So Professor Daniotti would share his screen if it works, and he would share your presentation. Let's see if it works. Yeah. Okay, so you should see your presentation shared by Professor Daniotti. So what we can do is, okay, and you just tell us next, please, or something like that, and Professor Daniotti will advance the slides, okay?
Okay. Okay, right. Perfect.
So
Thank you.
The floor is yours. Thank you. 15 minutes.
Okay. Well, hello everybody. Good day. This is a presentation of the thesis that I'm doing, or the work that I did for the past 6 months, maybe or more, because of the Corona situation, and it revolved around an exercise in convergence. Convergence is the main umbrella that holds the exercise under it. I can go next. Okay, this is an introduction of what is the exercise and how the thesis work was done and carried on. The exercise is a research and study assessing and evaluating not all, but many conversion facets through the design and related subjects that complement a particular concept of nomadic architecture. The information and the notes found in this work were meant to be a foundation that can be built upon to act as a design guide, at least for me as a professional, and in respect to the case study studied in the exercise itself. The exercise main purpose was to validate the first steps in the path to convergence. The main challenge was to gauge how convergence gradually develops in building design, or how it is revealed in areas like climate design and energy modeling, by exhausting a very consolidated tool. It's a myriad of tools actually, but we can call it like software of everything, and exhausting that software potential in design. It was concluded that convergence improves the flow of data, information, and knowledge, and the ease of use for and accessibility of a building designer toolset. Next, please. Okay, this is like a description of the whole body of work, the idea and the definition. It was a collection of knowledge and an extensive search, and the concept was a design concept as an open case study, put in different locations, comparing in a horizontal fashion many different criteria for a building design and building engineering. The tasks were combining many titles studied in the courses that I studied in the past 2 or 3 years, like climate analysis, energy modeling, parametric and integrated design, building physics, and structure analysis, etc. Of course. The target was to study the idea of convergence in building design, considering construction and operation consideration, of course, like the lifetime of a building, from design to operation, and even demolition and maybe retrofitting also along the path. So it's like it goes into a very everything, like generally speaking, about lots of fields of how a building should be and be designed. The main target was to study the idea of convergence, and yeah, I said this, yeah. Building a huge analysis canvas for design in convergence mode. So considering all aspects of design, if I can say so, and to provide a sort of a step-by-step guide in respect to the case study that can serve as a developing guide of a design of my own taste and experience in design and architectural and building engineering. The body of the thesis consists of three parts: convergence and what is convergence, and how it's sort of applied in design and the whole building industry. And the second part, the second part consists of 7 sections: energy modeling, and climate analysis, building physics, and so on. And the conclusion, which sort of like a show of what was the result and how actually we can have a theoretical guide that can lead a building designer through that this whole idea of convergence in building engineering. Next, please. The intersections. The knowledge of and understanding of convergent facets and intersections leads to paradigm shifts in the AECO industry. Many factors and concepts and intersections between them are critical in understanding what is convergence and how to find out the limits of what a building designer can do. So it's like it is how to understand all these intersections was critical at the beginning, and how to lay them out and see how it's flowing and how all these intersections are coming together. Next, please. A main idea and concept of convergence is the linear process versus the iterative feedback loop. Instead of a potentially stagnant linear process for design and construction of a building designer should work with the frame of iterative feedback loops that provide not so much instant result, but very accurate and certain knowledge of what we can do. Next, please. There's something called the bottleneck of convergence, which is a way of understanding how convergence actually is achieved. So many factors lead towards an end, which is convergence, and how these factors are organized and actually laid out is very important because it really shows the limits of what the environment of design can be, and how to reach convergence via it, through it, I mean. Next, please. Well, this was like the ideas and concepts behind every design, and how it's becoming increasingly difficult to match and mix and match all these concepts and ideas in the building industry, and how to organize and how to layer every concept in order to reach an optimum design. So all these ideas and concepts were actually studied or at least thought about and considered. Next, please. This is the architecture of the case study and how it was actually laid out. So it's just showing at the envelope and how it's described and how the design actually is affected by a very major item, which is the glazing ratio or the window to wall ratio, which is very critical. And I know it from the start that this would be an important factor, for example, among many others, but this was by doing the design, I discovered that this is a very, very critical thing to consider in many areas, because it really affects the energy modeling of the design and how actually all the decisions can be built upon, considering materials and lots of technical ideas, and how these are actually done in the architecture itself. Next, please. And the structure, there was in the exercise, I did sort of a structure analysis exercise. I did structure analysis for all the design itself by a software called Caramba. It is, as I said in the beginning, there's a tool set combined into one software. We can call it the software of everything, which was Rhino and Grasshopper and its plugins and its design tools. So this is just showing how the structure was laid out and how it became compatible with the architecture and the prefabrication idea, which minimizes lots of design times and cost and construction costs and liabilities and so on along the lifespan of the design or the building itself. Next, please. This is a progression of what happened to reach convergence in design. So it's like putting. So it's a progression of how elements are arranged for construction and how everything comes together. And of course, this is after many trials. So this is the result. So in the comparison itself or the base design, there were many ideas that were not shown here. Of course, they maybe are shown in the thesis itself. Next, please. Yeah, this is just to show and act as a proof of how a tool that we can call the software of everything that can house all the data streams and organize the data and into one algorithmic design environment, which, as I said before, is an advent of the software of everything, which we are progressing towards. And also how a building designer should put and organize data coming from all sectors of the building design and construction industry. And with the click of a button, you can run a study or design a material or actually lay out the function of the building or the program of the building. It doesn't apply, all of this has been applied in the design, but as the design case study itself is like a small to medium size, so many more factors and items can be considered, but all of these are showing in front of you are like the structural analysis, the glare analysis, daylighting, climate analysis, temperature, and all the environmental parameters of the 3 locations that were chosen in the comparison for the same building put into 3 different locations as I outlined in the beginning. So it's just a show. Yeah, this was an example of how psychrometry can actually help us design and integrate passive design strategies, and each strategy contribution to the comfort intended at hand or intended by the designer. So this is a show of convergence where we can have passive design strategies in mind as an architect working with an engineer or a mechanical engineer that can design passive and active systems, which is the next slide, shows how this was like for the passive design. So this is the potential active systems or active or mechanical systems that can be put for the design for each location. So it's just a show of how can design can at first, I mean, or in this exercise studied, we can have many potential strategies and concepts for mechanical, which complement the passive design as a first important step that has to be in any building design. So it's a show of convergence, but on a mini scale. Next, please. Okay, so as a conclusion for the comparison, I did have like a sort of a tiny report, and it acts like a canvas for decision making. So it's very important, and nowadays, of course, and it has been all the time, of course, for building design in the building design industry and engineering and architecture, is that many decisions are made in the wrong way, and they are not considered considered the beginning of the design. So by running an exercise like this, we can have sort of a canvas of the decisions to make. And these were a result of the comparison that I simulated or I did in the work. And now when I have this tiny report, I can now choose optimally what I can have for the design along the building lifespan from beginning to end. So it's like a consolidated report or tiny decision-making tool, if I can say so. Next, please. This is the design showing the design itself. It's a very simple design. It was built upon the idea of modularity and how everything shall come together in a modular fashion, and how it really can be effective to converge ideas of nomadic architecture and prefabrication in construction and all that to attain the optimal design and cost and so on. Next. This was a breakdown or a sort of a detail of how a module of a building can be. All this module is one of 12 for the building design that I studied or did, and it encompasses many different ideas that are written here on the left, but I don't think I have the time to show every idea. But what I can say is that in this small section, there are many different ideas which came about by convergence, and how a design can be designed optimally. Next, please. I think we're coming to the end. Yes, so in the upper part, this was the intent from the point of view of an architect on how to do sort of a nomadic architectural design. And at the bottom, this was the design conclusion that I did via many exercises, many simulations done to reach an optimal architectural, well-built engineered design. So it was sort of this whole exercise was sort of in many ways a theoretical and practical show of convergence, and I was able to validate many paths to convergence. I believe that every building should be aware of, and how this wide environment of information can come together and can give us and we cannot be lost in it. It's like a sea. So by knowing all these limits of that sea, we cannot drown in, if I can say so. So thank you very much. Hello?
I'm sorry. We had closed the audio of the room. You should.
Okay, now I hear you.
Yeah. So I was saying thanks for the for your elaboration, your presentation, and your elaboration on the concept of convergence, which is at the basis of also what we do in this master program and the reason for its existence. I have
Yes.
a general comment. I don't need an answer from you, but it's a general remark. It seemed to me that you have elaborated on this idea of convergence, and you have showed how you can apply that through parametric design tools, and you've done this exercise. I had the general impression that you were kind of struggling to bring all the knowledge to one place in a way. So to empower a single designer to go through a series of aspects.
Yes.
Don't forget that, of course, professional life is now strongly team-based, and it is very rare that you have a single designer gathering all the information and taking decisions. More kind of like a network. So it's more like convergence in different places. So it's a kind of convergent divergence. I don't know how to say that, but
yes,
it's kind of like, empowering different teams to take decisions, but at the same time having the ability to share this information.
Yes.
And the information flow, in fact, is one of the main, I would say, barriers or places where you have friction nowadays in integrated design processes. So that is my general comment, just to add a little bit to the discussion here. So anyway, thank you. I think that we have to close here because we are running out of time, and we have to go through. So thanks for your contribution, Ahmet.
Thank you very much. Thank you.
Okay, so we close this meeting for 15 minutes. So, and at 2 p.m. we will have the final ceremony. Okay, so you will see a different room, much better than this, and we will have the conferral of the word and the final proclamation. Okay, so okay, now we close the room, but not the connection. So don't just wait for us. Okay, 15 minutes, and we will be back to you.
alla risoluzione politica, la valutazione delle aspettative del Parlamento, è necessario modificare e in vigore in modo permanente prima della sua scadenza. La campagna vaccinale, nonostante i ritardi nelle forniture, ma anche grazie all'arrivo l'accelerazione della fase
È la distribuzione alle regioni dopo di vaccini Pfizer raggiunto nelle ultime ore in Italia, il più consistente dall'inizio della campagna di immunizzazione, 2.200.000 dosi per recuperare il terreno giorni, in cui si è registrato un rallentamento rispetto al record delle 135.000 somministrazioni segnato la scorsa settimana. Se le norme saranno rispettate nei prossimi 7 giorni dovrebbero arrivare a 7 milioni di dosi, 15
Io l'ho messo Anto, e ci disattiva. Devo
Sorry, social.
Can you hear me at home?
Yes.
Can you hear me? Please? Please? Yeah.
Yes, we can hear you.
Great. Can you see us?
Can you see us as
Yes.
well? Because we are not able to see us.
We can see.
Do we look great? Yes. Okay, good. Good answer.
Maybe, I don't know if it's just me, but there is an echo.
Okay, we can. Okay, so welcome to you all at Politecnico di Milano. Today we are really glad because we are in a brand new classroom, which is in one of the building of the new campus renewal by a project of Renzo Piano, who is an alumnus here at Politecnico di Milano. So we are really proud even to be here this morning. And we would like to give our warmest welcome to your families in particular and your friends who are, let's say, joining us remotely because of this situation. Of course, I just want to say on behalf of my colleagues that this is not the way we would like to celebrate with you this time, because of course it's a time of joy. So it's beautiful to see, even to share this joy together with you and your families and parents and relatives. But unfortunately, this is the way we can do that. And so I would like to say hello to all of your parents and relatives and friends who are following this ceremony at home. I'm introducing myself. My name is Giuliana Iannacone. I'm the head of the master program in building and architectural engineering here at Politecnico di Milano. And together with me for this final ceremony is, I start from Professor Graziano Salvalai, Professor Andrea Mainini, Professor Matteo Gastaldi, and I'm ending with Professor Gabriele Masera, who is the Deputy Dean of the School of Architecture, Urban Planning and Construction Engineering. Maybe we can have a short translation. Andrea, okay.
Buongiorno a tutti, abbiamo il piacere di essere finalmente qui presenti per il conferimento della vostra laurea dopo il percorso di studi che avete affrontato con passione, dedizione e speriamo anche piacere. Siamo molto onorati di avervi qui, come di avere i vostri parenti, amici, genitori che purtroppo per via della pandemia non sono presenti in persona, ma si spera che ci stiano seguendo a distanza e che ringraziamo per essere presenti e per avervi accompagnato anche in questo percorso. Vi presento la commissione di oggi. Abbiamo il professor Graziano Salvalai, il professor Matteo Gastaldi, io Andrea Giovanni Mainini, la professoressa Giuliana Iannacone e il professor Gabriele Masera.
Okay, the time being, we will be really short in this presentation today, but we just want to, let's say, remark some points which are related to the relevance of this graduation today. First of all, because you are graduating at Politecnico di Milano, we are really proud of being a leading university in Italy and even more in the world, especially in some fields, which are the fields related to built environment. And this is, of course, really appreciated by the job market because we have our work is really appreciated, and your competencies, the competencies that you have gained here, are really appreciated everywhere in the world. So we are sure that your future career will be really successful.
Vi ricordiamo l'importanza della giornata odierna perché vi state laureando al Politecnico di Milano e riteniamo che questo sia un valore aggiunto, anche perché il Politecnico di Milano è una delle università più rinomate dal punto di vista sia a livello internazionale che nazionale, e pensiamo che questo sia un valore aggiunto anche per il vostro futuro, perché il mondo del lavoro riconosce l'importanza del titolo che voi oggi state acquisendo e vi servirà appunto per essere riconoscibili e spendibili sul mercato.
During these 2 years, you have been trained to work in, let's say, with complex projects, and and you have been trained even to be able to apply advanced digital modeling tools in different fields of engineering, and this is a skill even that which is appreciated again for your professional career. And you have been trained also to deal with the complexity of the construction sector, working in team. So sometimes it's something that you are not really able to appreciate at the moment, because of course working in teams means to be able to manage conflicts, but this is a really important skills that which is called soft skills, which is again really appreciated in your future career. And one more aspect is that you have been trained to manage complex problems, working in team, and working into multidisciplinary and international teams, because of course your teammates have different background and come from every country of the world with different culture and points of view. Please switch off your microphone at all. Thank you very much. I promise I'll be short, so don't worry.
In questi 2 anni avete affrontato delle tematiche complesse, avete imparato a relazionarvi con la complessità e avete avuto modo anche di confrontarvi con tecnologie all'avanguardia, soprattutto relative al mondo della parametrizzazione e della digitalizzazione. Ma non soltanto questo, in questi 2 anni avete avuto anche modo di imparare a delle conoscenze delle competenze che noi chiamiamo soft skill, ovvero la capacità di relazionarvi con i vostri colleghi, la capacità di gestire i conflitti, la capacità in un progetto complesso di riuscire a organizzarsi nel modo migliore per raggiungere uno scopo comune. E questo l'avete fatto con grande difficoltà nei primi momenti dall'inizio della pandemia, che avete dovuto lavorare a distanza, e poi piano piano trovando un nuovo metodo, ma riuscendo alla fine comunque a raggiungere quello che è il vostro obiettivo di riuscire a portare a termine progetti che vi avranno sicuramente appassionato, ma come abbiamo detto sono stati complessi. Quindi anche questa competenza spesa in un contesto internazionale come quello che avete vissuto vi preparerà per il vostro futuro da professionisti.
Today is not a real farewell, but it's just a bye-bye, because after your graduation, we will be part of the, let's say, of the huge community of alumni in Latin, or alumni in English, which is the network of graduates of Politecnico di Milano, which is a worldwide network, a huge network with several professionals. And you will be able to meet these professionals in the different countries, because they work almost everywhere. And you will have again the opportunity to meet us again if you decide to continue with your PhD, the career here at Politecnico di Milano, or even to attend one of the possible courses of the continuing educational program offered here today.
Quello di oggi non è un addio, ma è assolutamente un arrivederci, e speriamo che appunto sia così. Ovviamente una volta laureati entrate a far parte del network degli alunni del Politecnico di Milano, un network molto esteso, internazionale, a cui vi consigliamo di appoggiarvi nel caso abbiate delle richieste particolari o semplicemente voglia di collaborare con quelli che sono i vostri colleghi o chiedere un supporto, un aiuto. Il vostro percorso con noi, o il piacere di incontrarvi, appunto, come dicevamo, non finisce qui. Avrete la possibilità, se vorrete, di seguire percorsi di dottorato e quindi di continuare a vederci tutti i giorni nei vari dipartimenti del Politecnico di Milano, oppure partecipare ai corsi per professionisti di formazione continua che vengono erogati dal Politecnico di Milano e che possono essere seguiti dopo il conseguimento della laurea.
So just a final big thanks to your families and friends who supported all your efforts during these 2 years, because we know how much effort is demanded at Politecnico di Milano to be able to be seated here today to get your diploma. So, un grazie davvero di cuore a tutte le persone che in questi 2 anni vi hanno sostenuto in questi appunto 2 anni di studio faticoso. Noi sappiamo perfettamente che è uno studio faticoso, e quindi vogliamo ringraziare tutti quelli che in questo momento ci stanno seguendo da casa, come si dice in televisione, o che sono attaccati qui alle finestre cercando di partecipare in qualche modo a questo momento che purtroppo non è accessibile ad altri che non siano gli studenti. Allora, procediamo. So let's move with the most interesting parts. So with the final mark. Adesso noi condividiamo lo schermo con condividiamo lo schermo. Now we are going to share our screen with the things that for you, okay, you are interested most. The final mark. Ta-da! So what we are going to do, we are calling one by one, and then if they are in the room, they can come here and keep the diploma. Okay.
And then they have to sign.
They have to sign a document they already have. So when you come here, you see, okay, when you're here, raise it. Okay. Okay. So stand up, give your, no, not now. When I call your name, you stand up, bring your white paper, give the white paper to the girl, nice girl with the red, and then you come here, you bring your diploma, and then go back. And the tube.
And then you roll the diploma and you put it in the tube if you like. If not, you hang it on your wall. Mine is in the tube.
Okay, let's start with Alice Benedetta Abbiati. Bring your paper. She also already have. Okay, sì, va bene. Okay. Architectural extension and performance analysis of a mountain hut in pre-Alps area, the Rifugio Lecco case study. Ta-da! 107, 107 su 110. Mostra le telecamere che da casa non ci credono, hai il diploma, gliel'abbiamo dato. Abdel Fattah Habiba Youssef Mohammed. Habiba, for me, bio-inspired facade design for urban island mitigation, from peacock feeders to daytime radiative coolers. 109. Do you want to say hello to someone else? Okay, it's your time to do that. Okay. Congratulations. Abhilash Kumar Mishra, analysis of monitoring data of a district system and comparison with mathematical model. 107. Alessandra Acquati, a comparative study of two BPS tools for the analysis of a dynamic facade. Alessandra, she's at home, right?
Yes.
Okay. 105. Thank you. Kevin Nautelitano, application of drone-mounted video and thermal cameras for building digitalization and diagnostics. Are you at home, Kevin? I guess so.
Yes, I'm at home.
Yes. 105. 105. Rafaela Belmonte Monteiro, building massing and performance, a guideline for early stage design, analyzing energy demand, daylighting and solar power. Oh, 109. Congratulations. Elae Beiranvand, application of thin film photovoltaics to the kinetics shading devices in buildings. At home, right? Maybe.
Maybe he's parking.
Elae?
Yes, I'm at home.
Ah,
Yes,
95.
yes.
Congratulations.
Here.
Maria Vittoria Borghese, aiming
Yes.
for outdoor thermal comfort, blah, 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 while mitigating
Poor Professor Maini.
the risk of increasing temperatures load through built environment resilience, but i suoi genitori vogliono sapere il voto, no?
Per questo ti diamo il voto.
Ah, ecco, sofferenza. 110 e lode. Piace?
Guarda come contento.
Brava.
Brava.
Grazie.
Riprenditi. Oife Callanan. Where are you, Oife? I know that I'm not pronouncing correctly your name because where are you, Oife? Study of physical and mechanical properties of GFRP bars through experimental testing. 106. Oife? Ah, ok, in Irlanda o in America. Ok, 106. Alessia Cannone, aiming for outdoor thermal comfort while mitigating the risk of increasing temperatures load through built environment resilience. Questa volta l'ho detta tutta. 110. Congratulazioni. Francesca Carla Codazzi. Adesso fatto piano perché così fa tutto il giro correttamente. Facades and Urban Environment. A framework for the assessment of the influence of facade design on the indoor and outdoor comfort for users. 110 e lode. Dario Dallara, Solar Energy in Low Temperature District Heating, Monitoring and Simulation of an Innovative District in Milan. Dario, ci sei? 110 lode.
Thank you. Dove sei, Dario?
Dario, fatti vedere, eccoti.
No, qui lo vediamo però.
Che gli amici e i parenti ti vogliono vedere per festeggiare.
Sto sorridendo. Va bene.
È contento del voto, direi di sì. Marco Enna, Panelization Design Parametric BIM Basic Tool for the Renovation of a Multi-Story Residential Building. 110 lode.
Grande Marco!
Marco è più moderato nella...
Gli ha perso un fumettino.
Ah, ok. Shin Yue-fu, Bionic Adaptive Facade Design, Evaluation of Adaptive Facade Design for Bionic Envelope System, inspired by Ladybug Wings. Hi, hi. 102, 102. Congratulations. Howie Mahmoud Geletu or Geletu, I always forget how to say that. Evaluation of daylighting distribution in office buildings. A case study. 104. Congratulations. Kaleab, Kebede, Geta 1 or Jeta 1? Geta 1, okay. Bio-inspired facade design for urban hail mitigation from peacock feeders to daytime radiative coolers. 110.
Caleb.
Zainab Hajimiri, guideline of zero energy houses for different climate zones of Iran. Are you here? Zainab?
I'm at home.
Hi.
Hi.
103. Rahul Krishna, Harikumaran, the effect of natural additives on properties of earth-based materials for sustainable buildings. We can see you.
Yeah.
Up, up, 90. Ahmed Mohammed Karam, convergence and exercise.
Yes.
87.
Thank you.
Shande Roya Karami, the influence of solar control window films on energy performance in office buildings compared to shading systems. Roya?
Yes, I'm Marco.
Hi, Roya, good afternoon. We go. 102. Jia Dong Lin, bionic adaptive facade design. We
Yes.
already read, okay? 105. Federico Massa, supporting structures for a vertical axis wind turbine, comparison between hexagonal poles and lattice towers. 109.
Grazie.
For the waiting room. Sorry, the waiting room is always very big. Okay.
Lavanya Nayak, climate data, climate change, and building energy simulation based on multiple actual years. 107. Faramand Aisan Reza Sadeh, Dynamic Adaptive Buildings, Case Study, Sharifi House with extrovert-introvert characteristics and possible strategy to optimize buildings performances. 90. Mehmet Sahin, Energy Analysis of Milano Educational Building Asset, Intelligent Community Design, 95.
Thank you.
Rossella Scalise, a comparative study of 2 BPS tools for the analysis of a dynamic facade. 102, 102. Tutti gli italiani, vabbè.
No.
Britta Shallock, corrosion monitoring of the reinforced concrete structures of the Giuseppe Meazza Stadium in San Siro and prediction of the residual service life. 110.
That's good.
Harshit Singh, climate data, climate change, and building energy simulation based on multiple actual years. 106. Ramachandra Pachamaratejas, for me, Tejas, biomimetic responsive facade and integrated approach to optimize environmental performance. 93. You have to come here if you want to be, if you're, yes, this is the right camera. That camera. Maduri, Pretica. Ventilated facade design engineering supported by BIM and visual programming tools. 103.
That one.
Ziyuan Wang, Bionic
Yeah.
Adaptive Facade Design, Evaluation of Adaptive Facade Design for Bionic Envelope System inspired by Ladybug Wings and its implementation. 97.
Okay.
Last, Chan Zhao, the same. No, it's different. Application and performance analysis of off-site construction system for building energy retrofit. 98. Last.
Ta-da.
Ta-da! Okay, so basically you are not yet graduated, so please be patient. And in order to be graduated, we have to wait our final speech. It will be given in before in English and then in Italian. The Italian one is the one with which has let's say it's accepted by law. Okay, so you have to wait the second one before before celebrating. Okay, I would like to ask you all to stand up, and even to our students and candidates at home, please, whenever you are, in your room, in the kitchen, in the living room, in your garden, stand up. And I would like to ask Professor Maini to read the English speech.
So, considering the certificates of the exam given, considering the results of the final exam, as a member of the graduation commission of the master program in building and architectural engineering of Politecnico di Milano, by the authority vested in me by the laws of the state and in the name of the Republic of Italy, I hereby grant to you, who have been named, a Master of Science degree in building and architectural engineering. You, who have been named, may use this title of Master Graduate in Building and Architectural Engineering in the measure, method, and responsibilities envisaged under the law. In carrying out your work, you have already demonstrated the dignity that the profession of engineer entails. In the future, your goal should be to aspire to continuously grow in your scientific knowledge and your conscience, without bending to interests, impositions, or influences of any nature.
Visti gli attestati degli studi compiuti, visti i risultati degli esami di laurea oggi svoltisi, in qualità di coordinatore del corso di laurea in Building and Architectural Engineering del Politecnico di Milano, per l'autorità conferitami dallo Stato e i poteri conferitemi dal Rettore, in nome della Repubblica Italiana, conferisco a voi che siete stati nominati la laurea magistrale in Building and Architectural Engineering. Voi che siete stati nominati potrete avvalervi del titolo di dottore in Building and Architectural Engineering nelle forme, con le modalità e con le responsabilità previste dalla legge. Nell'esercizio della vostra attività dovrete operare con la dignità che la professione di ingegnere comporta, costantemente ispirandovi alle conoscenze scientifiche e alla vostra coscienza, senza soggiacere ad interessi, imposizioni e suggestioni di qualunque natura. Con questo la proclamazione è conclusa. Best wishes to you all. Now you are graduates.